Okay, welcome to the lecture here. We're going to continue on in chapter 12. We'll then roll into chapter 13, which I believe the notes should be up there. Give everybody a chance to get in here. Okay, so we've been really talking about kinetics since, well, the beginning, and we're going to wrap it up here. We sort of finished up last time talking about the idea of mechanisms, and remember that mechanisms are a series of sort of what are referred to as elementary steps and a possible sort of plausible way that a reaction can occur. So, as we talked about last time, not all reactions do occur in a sort of one step process where it just goes directly from reactants to products. Some reactions may occur in several individual steps, maybe two, three, maybe four, maybe some types of steps that are along the way in order to get from reactants to the products. And these individual steps are what are referred to as those elementary steps in a mechanism. And the idea here is a couple of things. In order for a mechanism to be sort of plausible or possibly good or bad type of mechanism, there's really kind of two things that sort of has to happen for it to be a possibly good mechanism. And the first thing is obviously when you add up all of this individual steps along the way, they do need to equal the overall reaction that you're looking at. So obviously, if you add up all the steps and you don't get that reaction that you were looking for, it would be a bad mechanism. If you add up all the steps along the way and they do equal the overall reaction that you're looking for, then so far so good in terms of it's a possibly good mechanism. Now, when you do add up those individual steps, everything on the left-hand side of the arrow stays on the left-hand side of the arrow. Everything on the right-hand side of the arrow stays on the right-hand side of the arrow. So very similar to, what you maybe did in Chem 50 with like Hess's law and those type of things, where you added up all the individual reactions to sort of build an overall reaction. Anything that's on opposite sides of the arrow, that's the same, can cancel each other out or reduce down. Now, when things that completely cancel out in a mechanism, so something that is formed early on in the mechanism and gets completely canceled out or used up and does not appear in the overall reaction, that is what is known as an intermediate that we talked about. So again, that's the important part of like the intermediate is, again, it does not appear in the overall reaction. So gets made early on, gets used up, not there in the overall reaction. Now, if you add up all those steps and it does equal your overall reaction, that's good so far, like I was saying. The other thing is for each of those individual elementary steps in a mechanism, you can write a rate law for each of the individual steps. And this is the only place really in kinetics where you can actually use the coefficient as the exponents or the orders. And you could write the rate law based on the reactants and their coefficients to the orders. And again, that's the only place you could do that. And the second thing that you need to see for something to be a good mechanism is the rate law for the rate determining step or the slow step in the mechanism, which is sometimes referred to as the RDS, needs to have the same rate law as the one that was found experimentally. So usually a lot of times in these type of problems, they will tell you the experimentally found rate law was this, or the observed rate law was this. And when you write the rate law for the slow step or the rate determining step, it should have the exact same rate law as the one that was found experimentally. And if you have a mechanism where everybody adds up to the overall reaction, you have a mechanism where the rate determining step or the RDS matches the rate law that was found experimentally, then it is plausibly a good mechanism for that particular reaction. As I mentioned before, it doesn't necessarily mean that 100% of the time that's sort of the pathway that it takes. It just is a possible pathway for that reaction to take place in that particular thing. Obviously, if any of those two things really don't sort of match the rate law or adding up all the steps, then it's not a great mechanism, probably not a good mechanism and stuff like that. So we sort of ended up here on this example, and just to kind of go over this example one more time here, just to make sure everybody's on the same page. We added up again here both of the individual elementary steps. These are both what are referred to as being bimolecular. They both have two molecules on the reactant side in each of the steps. And we were able to cancel out the NO3 and also the NO2 reduced. But as we talked about last time, as we just talked about, it is actually the NO3 is the only one that is the intermediate in this reaction. Again, because NO2 is found in the overall reaction. So although it did reduce down, it didn't completely cancel out. And again, that's the key for the intermediate. It needs to completely cancel out. We could write the two rate laws for each of these steps. And again, we could use the coefficients to write those rate laws for those elementary steps. So the coefficient here was 2 in front of the NO2. And that is how we got the rate is equal to K NO2 squared. That's where the squared part comes from. Here we have for the second step, as we did, the rate is equal to K times NO3 times CO. And in this particular case, the experimentally found rate law that was given to us is the rate is equal to K times NO2 squared. That match step number 1. And what that tells us is that step number 1, again, was the RDS, or the rate determining step, are essentially the slow step in this mechanism. So in terms of the relative sort of rates of step 1 and 2, like the last question was asking, step 1 should be slower than step 2 in this mechanism. Again, because step 1 has the same rate law as the one found experimentally, which means that should be the slow step in the mechanism. Any questions on any of that stuff there that we talked about at the end there? Okay, so let's take a look at another sort of mechanism problem here. And so in this mechanism problem here, we have an overall reaction, which is our guy on the bottom here. So this is the overall reaction that we're looking at. And this is the sort of experimentally found rate law. And essentially what we're trying to do here is we're going to try to figure out, is this a good or sort of bad mechanism? So there's a couple of things that are a little bit different on this particular one than the previous one. A, we got multiple steps happening. B, what we have here is some information given us next to each of the steps. First step is fast. Second step is slow. Third step is fast. So when we're given a mechanism problem such as this, and they're nice enough to label fast, slow, fast, we automatically know that the slow step here is our rate determining step. So that is our RDS, is that slow step in the mechanism. And you can find it very easily because, well, it was nicely labeled as slow. So what that means is if this is a good mechanism, the rate law for our slow step should match the rate law that was found experimentally. So in this type of problem here, where we want to try to prove or disprove that this is a good or bad mechanism, it's kind of like in math, right? I think maybe geometry used to do that. You used to kind of make proofs, right? You kind of know the answer, but you got to prove it one side, the other side. And that's sort of the idea here. We want to try to prove that this mechanism is a good mechanism. And the way we have to do that is really two things. Again, the first thing is we need to add up all the steps. And when we add up all the steps and get rid of things that are intermediates, do we actually end up with the overall reaction that we're looking for? So let's start with that. So if I put a line here and I add up all these guys together, I'm going to get some stuff that's going to cancel out. So let me see what's going to cancel. So looks like this guy here is going to cancel and this guy here is going to cancel. It looks like, let's see, the N2O2 is on the right-hand side here. The N2O2 is on the left-hand side there, so they will cancel. And I think that is about it. So again, everything on the left-hand side of the arrow is going to stay on the left-hand side of the arrow. Everybody on the right-hand side of the arrow will stay on the right-hand side of the arrow. So let's just kind of add up everything here. On the left-hand side, we have 2NO. We also have an H2 and an H2, so that gives us 2H2, and that takes care of everybody on the left-hand side of the arrow. Right-hand side of the arrow, we got 2 waters, and we have an N2. So just looking above, that looks good, that looks good, we got that, we got that. So right off the bat here, one of the criteria we need for it to be a good mechanism has been met. When we add up all of these 3 reactions together, these elementary steps, we do get the overall reaction that we're looking for. We could also see that in terms of intermediates here, it does appear that N2O2 is an intermediate, and N2O would also be an intermediate. Again, both of those things are made in the mechanism, but does get used up by the time the reaction's over and does not appear in the overall reaction. So far so good. We got a match in terms of the overall reaction when we add it together. The second thing that we need to make sure of is this right here, that the rate law for the slow step does equal the rate law that's found experimentally. So where we would want to start perhaps is the rate law for that slow step. So we want to write what the actual rate law is for step number 2. So for step number 2, which is our RDS here, we could write the rate law, and the rate would equal K times the concentration of H2 times the concentration of N2O2. And what we want to do now is take a look at this rate law here, which is for our slow step, and see, does it match the rate law that was found experimentally? Now, there is sort of a problem here in comparing those two things. It's kind of that old saying, you want to compare apples to apples, right? Oranges to oranges, whatever it may be. Chocolate chip cookies to chocolate chip cookies. Here, we can't really do that because in our slow step rate law, we have an intermediate. So it really doesn't allow us an opportunity to sort of compare, or compare those 2 rate laws in sort of their same fashion, where we pretty much have things that are in the overall reaction, right? In this case, we have an intermediate, doesn't appear in the overall reaction, makes it really hard to say for sure that those 2 guys match. So this is sort of where the proof part comes into play, or the math part here. What we need to do is use the other 2 steps, or maybe even just one of the other 2 steps. May use both, may just use one of them. But we need a way to get rid of the intermediate and substitute in there something else that's part of the overall reaction. So what we could do is, and what I'm going to do, I'm going to kind of clear up some of the, maybe clip some of the crossing out I did already. Let's kind of clear up some of that. All right, so let's get some of this guys out of the way as well. Give something to write with. Perfect. All right, so what we could do is we could actually write a rate law for the other steps. So for step number 3, we could say that the rate is equal to K H2 N2O. For step number 1, it is actually a reversible reaction. So it's arrows heading in both directions. And when a reaction is reversible, that means there's a forward direction and a reverse direction. So a forward direction heading from reactants to products, a reverse direction heading from products back to reactants. And at some point, it will reach equilibrium, which means the rate of the forward reaction will equal the rate of the reverse reaction. So at some point, a guy like this, the rate of the forward reaction will equal the rate of the reverse reaction. And because it is a reversible reaction, we actually can write not one rate law for this step, but we can actually write 2 rate laws for this step. One in the forward direction. So if we write the forward rate law, and that is like our normal reaction going from reactants to products, we would say that the rate equals K NO squared. And if you want to use the numbers there, that's K1, I guess. Don't really matter. And we could also write the reverse direction rate law, and that would be going this way. And when the reaction is going in the opposite way, our products become our reactants. So the rate law here would be the rate is equal to N2O2, or K times N2O2. So these are the two rate laws that we could write for this reversible reaction. Again, we could write two of them because it's going in one direction and also coming back the other way. And as it does the reverse reaction, our products become our reactants, which is why it's part of the rate law here. Any questions on that? Now, when we're looking at what we're really trying to do, we're really trying to get rid of the N2O2, right? We want to get rid of that because that is not part of the overall reaction. And if I look at the rate law that I wrote for step number 3, it has nothing to do with N2O2, which means really, I don't even have to worry about this guy because I can't really use it to help me out here. The only other one that has N2O2 in it is the rate law for the reverse reaction there for step number 1. And because the forward direction and the reverse direction at some point will reach equilibrium, what's going to happen is I could set each of these things equal to each other. So I could set the forward direction equal to the reverse direction. And when I do that in terms of the rate law here, I could say that the K1 of NO squared will equal K to the minus 1 of N2O2. And again, because this number here and this number here, although I don't know what it is going to be the same. And that's why I can set these guys equal to each other. That's beneficial because I am looking to solve for this guy. So I'm going to divide my K to the minus 1 to the other side. These guys will cancel. I now have something that I could substitute into my original rate law, which is this, can now go in place of the N2O2 in this particular case. So, hopefully it looks okay on the screen. Yes, everything's the right size. All that good stuff. Okay, so let's just kind of review. So I'm not sure where it cut off, but a reminder that what we're trying to do here is essentially take that rate determining step and the mechanism for it, not the mechanism, but the rate law for the rate determining step. And we want to compare it to the one found experimentally. And we have a intermediate that was in that rate determining step mechanism. So what we need to do is basically get rid of the intermediate, and we want to use the other steps in the mechanism and their rate laws to help us out. So really what we're looking to get rid of here was the N2O2. And in this particular case, the only really step that had the N2O2 sort of in it was the first step. So although I did write a rate law for the third step, I didn't necessarily need to use it because it didn't contain really the N2O2, which is sort of what we want to get rid of. So using the first step, which again is a reversible reaction, which means you do have that forward and reverse direction, and you can write basically two rate laws for it. Again, one going in the forward direction and one going in the reverse direction. And as you write the one for the one in the reverse direction, the products become your reactants. So that's how they get part of the rate law there for the reverse one. And because that's an equilibrium reaction, basically, or it will come to equilibrium, the rate of the forward direction will equal the rate of the reverse direction, which means we could essentially put those two rate laws equal to each other, which is essentially what we did here on the bottom. What we did right here. And by putting them equal to each other, we then can solve for the N2O2, which is what we're looking to solve for. And now, as you can see here, we could throw it into our original rate law for our second step and substitute it in. And that's, I think, where I got cut off there. So if we put what I circled here into the rate law, what we get is basically K times K divided by K times H2 times the NO squared concentration. Now, all those K's there, K times K1 divided by K to the minus 1, they're all really the rate constant, which means, although, again, we don't really know what the value is of that, we do know that they are the same number, which essentially means that two of them here will essentially cancel out. And what you'll be left with is the rate is equal to K H2 and NO squared. Now we have a rate law that has just the things in the overall reaction. We can now compare it to the one that was found experimentally. And what we see now is, although originally when we wrote the rate law for that second step, it didn't look like it matched at all. By getting rid of that intermediate and using the other steps, we now can see that, yes, it does actually match. The rate law for that slow step does match the rate law that was found experimentally. So really what that means is this is essentially a good mechanism. It pretty much meets the two things that you need to have met for it to be a good mechanism. When we added up all the individual steps, it did equal the overall reaction. And when we found the actual rate law for the slow step or the rate determining step, we do see that it does match. So if we got to a point where those two things did not match, again, would mean it was not a good mechanism. But here, because it did match, it does mean it's a good mechanism. Question on that there?
Okay, so Professor,
Yeah.
I'm still a little confused on how we ended out with the rate K equals to KH2N2O2. Because I was following up to the point where we were like canceling stuff out in the earlier part, but
Mm-hmm.
like I'm just not sure how we ended up with that in particular.
At the very end, you're talking about?
Or I
Yeah.
mean like
So
more
at
towards
the
the
very end, we ended up with it after we substituted in uh, the rate law for the other step. So let me see if I can find somewhere to scribble on here. Uh, go here. So our original rate law was H2N2O2, right? So we had, so for that slow step, we had the rate equals K H2 N2O2, and that was for the rate determining step. And this is ultimately what we were trying to get rid of. And what we had for the first reaction was that the rate, or the first step, was K times, it was the NO squared. So for the first step there, we had NO squared, and that was for the forward direction in that first step. And for the reverse direction, we had that the rate was equal to K times N2O2, and that was for the reverse direction. Now, so both of these came from step number one in the mechanism. Those are the two rate laws that you can basically write for that first step because it's a reversible reaction. So you got both directions happening. So you could write a rate law going from both ways. And again, because the rate of this reaction is going to be the same, because that's basically what it means when you have a reversible reaction, it eventually will come to equilibrium. And when something comes to equilibrium, what it means is you don't have equal amounts on both sides, but as fast as it goes to one side, it comes back the other way just as fast. And what that means is this number here and this number here is going to be the same number, which means I could set this guy equal to this guy, which is what I did. So K of NO squared would equal K of N2O2. And the reason I want to do that is because remember up here, what I'm trying to find is a way to get rid of that N2O2. So when I divide the K to the other side, which was K to the minus 1, I think, but put the actual number in there. This was K1. These guys will cancel. And that leaves me that the concentration of N2O2 actually equals K to the 1 NO squared divided by K to the minus 1. So this whole thing.
I'm sorry. Where did you get the K minus 1?
It's actually just a symbol, so it doesn't really matter the kind of the subscript, but right here. This is K1 going in this direction. And this is K to the minus 1 going in that direction. It actually comes from right there. You could just call it K. It doesn't really matter. You can put any numbers you want on it, but they're just really kind of, the K1 is for the rate constant going in the forward direction. The K to the minus 1 is the rate constant going in the reverse direction. Sometimes they'll even they'll call this one sometimes K2. They'll call this one K3, just so you have an idea as to sort of where it kind of comes from. So the really numbering of those things doesn't really matter. They're all essentially the rate constant, which essentially means they're the same value. They're all equal to the same thing. But sometimes in mechanism, they'll sort of number them sometimes, just so you can maybe keep track of sort of which one you're technically using at that point. Other questions on that there? So now that we have really what N2O2 equals, we're going to take that entire thing that's in the square and we're going to put it into our original rate law that we wrote for the second step. And if I do that, what I will get is K H2, and I'll just do it like in order here, K1 NO squared divided by K to the minus 1. So again, all I did is just take that and substituted it into here. These Ks, as I just mentioned, as we were just talking about, all these Ks, they're essentially the same number because they're the rate constant, which means they should be constant for this reaction no matter what the situation is. So although we don't know what it is, this K here and this K here will cancel each other out because they're dividing, which means what we are left with is K times H2 times NO squared. And this is the correct rate law based on getting rid of the intermediate in our rate determining step. And when we compare that guy to the one that was found experimentally, it does match. So that's how we know it's a good mechanism. So a lot of this, this type of mechanism problem is one where you have to kind of use the other steps and some math to substitute out the intermediate so that you could get a rate law at the end that contains things in the entire reaction so that you can compare that one to the one that was found experimentally and see if they match. So in this case, they did match, and that means that this is a a good mechanism, or how it's usually worded, a plausible mechanism for that particular reaction to occur. Questions on that? Okay, so why don't you try one and see how you do. The proposed mechanism for this reaction of 203 to 302 matches the observed rate law. The rate is equal to K O3 squared, O2 to the minus 1. These are the steps in the mechanism. So take a few moments here, work through it. So basically what you want to do is try to prove that this is a good mechanism based on the rate law that was found experimentally. So see what you come up with, and then we'll talk about it. Okay, so let's take a look and kind of see this. So again, remember, in order to sort of prove, if you will, and that's sort of what a lot of these mechanism problems kind of turn into, especially these type, um, that it's a good mechanism. Again, there's two things that you want to make sure that happens. Again, when we add up both of these guys, in this case, there's just two elementary steps, that we do get the overall reaction. So let's just start there. It looks like the O will cancel on both sides there. And that will give me 2O3 goes to 123O2. So that was the equation right here. The 2 is up there, so I'll put it here. So this does match. So far, so good in terms of it being a good mechanism. We have all those steps adding up. We also see that the intermediate here is the O. Now, in terms of which step here is the important one, it is going to be our slow step, right? So our slow step is going to be our rate determining step. And that one's the important one because in order for this to be the correct mechanism or a good mechanism, it needs to have the same rate law as the slow step as the one that was found experimentally. So if we write the rate law for this slow step here, we would say that the rate is equal to K times O3 times O. And again, we want to compare that to the one that was found experimentally. But just like the previous example, we have a little problem here because in our rate law here for our slow step, we have our intermediate. And again, we can't really compare them at this point because it's not, again, that apples to apples sort of comparison. So just like last time, we need to use some other steps in the mechanism to figure out the actual rate law and kind of get rid of the O. And to do that, in this case, we only really have step number 1 to work with. It also is a reversible reaction. So we got the K1 going in that direction, K to the -1 going in that direction. So we can write two rate laws for step 1, just like we did in the previous one. In the forward direction, which would be reactants going to products, we could say that the rate equals K1 times O3. Now, in the reverse direction, going from products to reactants, our products become our reactants. And that would be the rate is equal to K to the -1, O2, and O. Any questions on how I got the rate laws there? And again, you're just basically writing two rate laws, one for the forward direction, where obviously the reactants are your reactants, and one for the reverse direction, that reaction where your products become your reactants in the reverse direction.
What is it that we're trying to do with the rate K03, the one on top?
Yeah, the purpose of what we're trying to do is we're trying to use this step in the mechanism to help us get rid of the intermediate here, because we ultimately want to compare the rate law for the slow step to the one that was found experimentally, but we can't do that because the rate law for our slow step has an intermediate in it. So we need to get rid of the intermediate through math, basically substitute out the intermediate for something else that is found in the overall reaction so that we can compare both of those rate laws to each other. So right now, we really can't compare it because we have that intermediate in there.
Okay, but what is, why is that equation given on top, the one that's rate equals K03? Like, are we comparing it? Is it telling us that that is what we should get?
Are you asking why we have this reaction or this
No,
reaction?
the one that you squared on the top.
The one that I squared.
The rate equals K 03 to the second power and then O2 to the -1.
Oh, this one right here. This was given to you in the problem because this is the experimentally found rate law. And the experimentally found rate law is important because in order to verify that the mechanism you're looking at, which is that step 1, step 2, that mechanism that you have there is the correct rate law. In order for it to be like a correct rate law, I'm sorry, a correct mechanism, the slow step in the mechanism should have the same rate law. So in these mechanism problems, a lot of times they will give you the experimentally found rate law, which is this guy. And your goal is to go, this is the rate law for the slow step. Do they match? And if they do match, what that means is this is possibly a good mechanism. If they don't match, then it's a bad mechanism. So that rate law that's given to you there, that's in the box, is really important because that is the one that's found experimentally. And in order for you to prove that this is maybe a good mechanism, the rate law that you find for this mechanism needs to match it. And if it doesn't match, then it's a bad mechanism. If it does match, it's a good mechanism.
So in this case, would it be a good mechanism or a bad mechanism?
That's what we're trying to prove. So we kind of know the answer, but part of what you have to do is you have to mathematically here and use the mechanism, try to prove that it's a good mechanism or a bad mechanism. And the reason we can't just right off the bat use this rate law from the slow step and compare it is because we have this intermediate in there. And that means we can't really compare that rate law to the one found experimentally, because in the one found experimentally, the intermediate is not present in the rate law. And it shouldn't be, because it should, an intermediate gets used up by the time the reaction's over. So the purpose of this is you need to kind of prove it through sort of math and substitution that do you have a rate law that really matches? And that's sort of where we're going with this. Is the ultimate goal here is we want to kind of get rid of the O in this case because it's an intermediate. So we want to find a way to substitute out that in the rate law.
Okay, got it. Thank you.
You're welcome. Okay, so that's really where we're at. Again, as we were just talking about, the goal here is we need to get rid of this intermediate in our rate law. So in this case, that is our intermediate. And because the forward direction and the reverse direction will eventually equal each other, we could set both of those rate laws equal to each other. So we could say that the K1O3, which is basically the forward rate law, will equal the reverse rate law, which is this guy. Now, again, here, what we're ultimately trying to substitute out for is the O, which means just math here. We're going to divide this to the other side. This is all going to cancel. And what this is going to give us is K1O3 over K to the minus 1 O2 equals O. And that is, again, what we now want to take and substitute into our original rate law. So we basically want to take this thing here, because what I'm boxing right now basically equals the concentration of O. And we're going to take it and put it into our original rate law that we wrote. And if you do that, you will end up with the rate is equal to K03, K to the 1, O3, divided by K to the minus 1, O2. And if you just directly just slap that in there, you could do some cleaning up. So at this point, all the K's are the same. So these two are going to cancel. I have O3 and O3. That means that essentially, if I kind of clean it up, I have K to the O3 squared divided by O2. So now we have a rate law that's here that we can compare to the rate law that was found experimentally. And what we want to determine is, do they match? And hopefully you know that they actually do match. That's the same thing. So O2 to the minus 1 is 1 over O2. That's how it gets to the bottom. So that's what the minus 1 represents there. So in this case, they actually do match. And what that means is that this is a possibly good mechanism, a plausible mechanism for how this reaction could take place. Again, doesn't mean it always takes place this way, but it is obviously a sort of pathway or a possible way that this could take place. Again, because the overall reaction, when we added up all the steps, equals the overall reaction we're looking at. And once we finally got a rate law that contained everything in the overall reaction in it and had no intermediates in it for the slow step, the rate law for the slow step did indeed match the one that was found experimentally. And that means that this is a good mechanism. Any questions on that?
Professor, when you have a negative exponent in the rate law, what would you call the order of that one?
It is it's a good question. It would basically be it would be the it would be called negative. It would actually just be called -1, I guess, is the way you would word that.
Okay.
Yeah, in that particular case. Yeah. Other questions? Okay. So these are a little bit more involved type mechanism problems, and ultimately they're kind of like problems. They're essentially proof type problems. So you sort of know, which is sort of the guy in the box there, the experimental rate law that they give you, and you need to use the mechanism to prove it. So usually that includes some type of math like this where you have to substitute things in. And the goal is really, if you have sort of that intermediate in that rate determining step, you need to get rid of it so that you can compare sort of apples to apples, everything that's in the overall reaction to each other. Other questions on that? Okay. So I could barely see it on my screen here, but it looks like there's something there. I think what we got going on here is, why don't you give this one a go? I'll kind of scribble over it. A plus B to the 2 goes to AB plus B. This is slow. And A plus B goes to AB, and this is fast. All right, so why don't you give this one a go again, another type of mechanism problem here. Determine the overall reaction, the rate determining step, and what the rate law for this mechanism should be based on it. So take a couple of minutes, see what you come up with.
To go directly across the gradient, wouldn't the equation, wouldn't you need to have a reversible reaction?
Say it one more time. I'm sorry. To go.
To go across to like make any mathematical transferable equations, wouldn't you need to have a reversible equation?
You would usually. So you need some type of reversible equation. And in this particular case, you won't need to do that actually. So, but yeah, you typically do need that reversible equation to kind of have something to substitute in. So let's take a look at this one here. So this one's a little bit different. We're not actually given a rate law experimentally. We're actually asked to find the rate law based on this mechanism. So this is a little bit different of a mechanism problem like the last couple that we did. The last couple that we did, we were given an equation, we were given an experimentally found rate law, and we were essentially asked to prove that this was a good mechanism or a bad mechanism. So here we're actually just asked, what is the overall reaction? And based on this mechanism, what we would expect to be the actual rate law that should come out of it. So in doing so, the first thing's pretty easy. We're going to just add up all the parts here. We're going to cancel out anything that should cancel. Looks like B here will cancel. And I believe that should be it. That will leave us with 2A plus B2 goes to 2AB. So this would be our overall reaction based on this mechanism. Now, in terms of the rate determining step, it would be this guy here, the first step, because it was labeled the slow step. So we know that this would be our rate determining step. We also know that for a mechanism to be correct or a good mechanism, that the rate law for the slow step or the rate determining step will have the same rate law as should be found experimentally, which means if we needed to write a rate law, it would be equal to the first step in this case, which would be K times A times B to the 2. And this should be the rate law based on this mechanism, because this is the rate law that we get for our slow step. And I think the last thing was, it looks like B was our intermediate here in this particular case. So this is, again, a slightly different type of mechanism problem where you're just kind of given the mechanism and they ask you, what would be the rate law based off of this mechanism. And obviously they would have to label it slow or fast in order for you to determine which one would be the rate determining step in this case. Question on that one. So as you can see, there's a few different sort of types of mechanism problems that you may come across. So you do want to make sure you read it really carefully. And again, like the question was asked, usually the ones that will involve some type of substitution like we did in the previous two problems, in that mechanism, you probably will have a reversible reaction happening somewhere. And that's definitely usually, I would say, always the case, because as was mentioned, that's pretty much almost the only way you can kind of substitute something out for it. Any questions on mechanisms? Again, these are possible ways reactions could occur. Again, doesn't mean they always occur this way, but it's usually the word, like I said, that is commonly used with these is this is a plausible way that this mechanism or this reaction could occur. Any questions on mechanisms there?
I have a question.
Yeah.
For mechanisms, if I'm not wrong, I think you said the coefficients can be the orders, right?
Yes.
So wouldn't it be a squared, like a to the second order for the rate law? Because
yeah. So I think you're asking if you wrote the rate law based off of the overall reaction, right?
Yeah.
And you won't do that. The rate laws in a mechanism are written based off the elementary steps individual. So this rate law here came from step number 1. And it's only the elementary steps, which are these individual steps, that you can write a rate law and use the coefficient. So that's the only place that you could do that. So I could technically have wrote a rate law for the second step, which would have been the rate is equal to K times A times B. But this rate law here for the second step is really not important because it is always a slow step that's really the most important one in a mechanism. So we wouldn't write a rate law based on the overall reaction. We would only write rate laws based off of the elementary steps, each of the individual steps in the mechanism, and use those coefficients as those orders. And again, that's the only place that you could kind of do that is not for the overall reaction, but for the individual kind of steps in the mechanism.
Okay.
Sorry. So in this, like right here, it's asking to find the rate law. So would that be the rate law that it's asking for, or is it what you were just explaining?
The correct rate law for this mechanism would be this original one here I boxed.
Got it.
Because whenever you have a mechanism, there's always maybe 2 steps, 3 steps, 5 steps, however many steps there are. But the most important one in a mechanism is always the rate determining step or the slow step, because that's the one that's really going to determine how fast the overall reaction will take place. So the slow steps rate law in a mechanism is the one that should be really the overall rate law for that reaction when it's all said and done. And that's why when we were talking about earlier on in this chapter that we don't use the coefficients, right, for the rate law, because as you can see here, the coefficient for A is actually 2, but really based on how this reaction actually takes place, the order for A is really first order, right, as you can see here. So they don't match. And that's why earlier on in the chapter when we talked about you don't use the coefficients as the orders, this is exactly why, because not all reactions happen as they are written in the overall reaction going from directly reactants to products. So what you can see here is this is a 2-step mechanism for how this reaction actually takes place. And if you write a rate law with the overall reaction, which is this guy here, you would be tempted to write it as what the question originally was, the rate is equal to K A squared and B to 2. And this is really not correct in this case because of the way this reaction actually takes place. The actual order for A is, as you can see here, is actually only 1. And that's why pretty much 99% of the time when we're dealing with just the overall reactions, which is pretty much everything we were dealing with before we got to mechanisms, we don't use those coefficients because, again, these steps do occur in multiple sort of processes. And we need to really figure out which part of that process is really the one that's holding up the line, like the 10 items or less sort of example I did the other day. In this case, it's step 1 that's really, it's the slowest part. It's the part where you're like tapping your feet, waiting for it to happen. And then it finally happens. And then the rest of the steps happen relatively fast. So that's why we can, in a mechanism, use the coefficients because each of these individual steps or one of these individual steps is super important in the overall rate of the reaction. But when we kind of clean up all the individual steps and just look at the overall rate law or the overall reaction, we don't really know which step along the way is important by looking at the overall reaction. And again, that's why we can't use the coefficients from the overall reaction as the orders, but we can do it here in the mechanism part of it. Other questions on that? Okay. Oops. All right. So again, like there's a few different types of mechanism problems, and the important part to remember really is those 2 things. When you add up everything, it needs to equal the overall reaction. Or in a problem like this, when you add up all the things, the reactions, that is the overall reaction. And secondly, the most important part of a mechanism is that rate determining step, because ultimately that is going to be the rate law for the overall reaction. All right, so let's finish up this chapter here, I think. Just a little bit about a catalyst, and I think we talked a little bit about it earlier, but a catalyst is really a substance that will increase the rate of the reaction usually. A catalyst can actually slow down a reaction. They're sometimes referred to as a negative catalyst, but probably 99.9% of the time if somebody mentions I added a catalyst or something to a reaction, Usually they're talking about it in the I'm speeding up a reaction is usually what they're referring to. And what is a catalyst? A catalyst is, as mentioned, it's not a reactant. So it's not a reactant. It's not a product. And it does not get used up. So it is there after the reaction's over. And again, not considered either a reactant or a product. It is really there just to facilitate a reaction happening quicker in most cases. And that may be it's maybe a solid catalyst where it allows things to sort of migrate to and allows them to come together quicker. It may actually be a catalyst that's floating around in a solution and just kind of helps everybody kind of come together, the reactants, in a more efficient manner. And what it ultimately does, though, in terms of you look at, say, an energy diagram like what we see here is, if you remember, really the rate is going to be determined on this activation energy. So that hill that those reactants has to climb to get to the other side. And usually what ultimately a catalyst does is it lowers the activation energy. So a catalyst will lower the activation energy. And as you can see over here in the catalyzed reaction, instead of having to climb way to the top and come on over, the hill is much, much smaller here, which means everybody could get to the other side usually a lot quicker. There's also a greater proportion of guys that are able to get to the other side quicker because that big hill that you had in front of them, you now cut in half or whatever it may be, dropped it down. They're able to get to the other side much, much faster. So that's really why when we put a catalyst in, the reaction will really proceed usually a lot faster because we really lowered that barrier down. So we lowered that hill that they have to climb to get to the other side. Now, catalysts can be several different types. A catalyst can be a heterogeneous catalyst. And in a heterogeneous catalyst, just like a heterogeneous mixture, it means that the reactants in the catalyst are in different phases. So this could be solids and stuff like that. And by the way, when you look at an equation, that is typically, you know, what you see kind of written on top of the arrow, platinum, maybe H+, which is like an acid catalyst or something like that. You know, so a lot of those catalysts will be written on top of the arrow. The Haber synthesis of ammonia is an example of that. The production of nitric acid is also an example of that. The ammonia is a spontaneous reaction, but it takes a very long time to occur. So the presence of a catalyst allows everybody to kind of come together a little bit more efficiently, and it allows it to happen a lot quicker. Catalytic converters in our cars, right? We got a couple of those in there to take care of a couple of unburnt, so hydrocarbons and pollutants that go through the catalyst. A homogeneous catalyst, just like a homogeneous mixture. Homogeneous mixture means that it's the same throughout. So this would be catalysts that are the same state as the reactants. So common ones are acid and base catalysts, kind of like the experiment that we're doing in lab, that HCl, kind of really a catalyst thrown in there, gets the H+ guys floating around with everybody else in the solution. Again, it just really helps it occur a lot quicker. A lot of times it has to do with the control of sort of the pH of the solution. And sometimes having control of the pH will make a reaction occur quicker and maybe make a reaction not occur as well if you kind of adjust the pH one way or the other. So here's an example of sort of the Haber process when we make ammonia and we have some solid iron, aluminum oxide, and potassium oxide. And again, here you can see the catalyst is a solid. Without the catalyst there, these guys are just going to be kind of floating around, flying around, trying to find each other. But they are sort of attracted to the metal here. And that also helps them kind of weaken their bonds between them as they sort of bind to the catalyst, and also it allows them then to sort of reassociate and, you know, make their new products over here and our NH3 guys are made. So the catalyst actually serves a couple of sort of processes here in this particular example. Again, it gives everybody a place where they're kind of attracted to, and as they sort of bind temporarily to that metal, it actually helps weaken some of those bonds and allow them to come apart and reassemble a lot more, I'll say, efficiently, I guess, than if they would without the catalyst, and they're just kind of, flying in the air there and trying to come in contact with each other. So again, without the catalyst, it's a very long sort of process that occurs. And this is the process here of making nitric acid, and platinum catalyst is used. And here, again, some ammonia, some O2, and it's a sort of a stepwise mechanism here. And the nice thing sort of about this stepwise mechanism is, as you can see, as we go and make this, we make some NO2. That NO2 then reacts with the water and makes some nitric acid, also makes some nitrous acid, which actually will go back through and kind of feed in some more of this as well in this sort of process. So it's a very sort of efficient way to produce nitric acid by having that, as you can see there on the right, hot platinum wire over some ammonia will make your nitric acid. And sort of the byproduct of making that nitrous acid is it will actually break apart and produce a lot of the starting products that you need for nitric acid. So you got this nice kind of double feeder sort of system that occurs. And there's our car and our catalytic converters. Again, burning some unburned hydrocarbons and some nitrous oxide and all that kind of stuff out of your tailpipe so it doesn't go into the environment and make it CO2 and water, as opposed to releasing sort of these unburned hydrocarbons into the environment. And again, one takes care of sort of the carbon emissions, one takes care of the nitrous oxide type conditions, and again, only lets sort of good stuff out of your tailpipe, which is why when you get a smog check, right, they probe what's coming out of your tailpipe of your car. All right, any questions on chapter 12? That should be chapter 12. A reminder that we are having an exam, no, we are having an exam eventually, but not soon. We are having a quiz, I think is a better way of putting that, on Tuesday on chapter 12. And again, I think we'll take it probably at the start of lab. So we'll have our normal lecture, I think, on Tuesday. And at the start of lab, we will take the quiz, and then we'll come back to lab and sort of do whatever we need to do. I think we'll still be continuing with that experiment that we're working on now. So that's sort of the game plan for that. Again, you're going to need to use, I think, on this quiz, Proctorial. So make sure, again, you finish that practice quiz so you have it all set up. Otherwise, I'm not going to have any sympathy for you if you tell me I can't get it to work on the real quiz. So make sure that you do that one. It is worth the points, and you get it working and operational so that you have no problems on the real quiz. Because again, if you didn't do that and you have problems, I'm not going to extend it or reopen it for you or anything like that. So make sure that you take care of that. Also, a reminder that you will not be given any type of formulas, but you will be given constant type values. Any type of constants or conversions you'll be given, but no formulas will be given to you. So you do need to know the rate laws and integrated rate laws like we've been talking about, all those type of things. Any questions on that there? Okay. So we will get started here then with the next chapter, which is equilibrium. And it is kind of the big topic of the season here. Pretty much everything is going to be about equilibrium in this class for the most part. And let us talk about it. So we touched a little bit upon it here when we're talking about sort of mechanisms here, chemical equilibrium. And when we talk about equilibrium, as I mentioned, when we're talking about the mechanisms, is sometimes people have sort of a a misunderstanding about what exactly chemical equilibrium sort of means. And first off, it does involve those reactions that we were just looking at. It usually involves a certain type of reaction, which is a reversible reaction. So as we were just talking about with mechanisms, a reversible reaction has arrows heading in both directions. It has a forward direction, and it has a reverse direction. And as we talked about there with mechanisms, what it means when something does reach chemical equilibrium is, it is really the rate is what we're talking about. It is the rate of that forward direction will equal the rate of the reverse direction. So what that means is, just as quick as it goes from reactants to products, those products then will go back the other way from products to reactants. And if you have something that's going back and forth at the same rate, what that means is when it reaches equilibrium, it doesn't mean that they have the exact same amount on each side. It just means that when they reach chemical equilibrium, whatever everybody's concentration is at that point, they're pretty much going to be locked into there. So for example, if we reach equilibrium and the concentration of A was 2 molar, 3 molar for B, 4 molar for C, and 2 molar for D. When we reach equilibrium, these guys will be able to be maintained, because just as quick as it goes to the right, it's going back to the left. So you got that equal flow, and it just locks everybody into place in terms of where their concentration was at that point, maybe their pressures, if we're talking about pressures. It doesn't mean when we reach equilibrium that we have hey, we got 6 molar on the left and 6 molar on the right, or the same amount of everybody. It just means that wherever they are in terms of their concentration at that point, they're going to be locked in, and nothing will happen to their concentrations. They'll be able to maintain those concentrations unless you did something to mess up the equilibrium, which we'll talk about later on in this chapter as well. So when we look at a solution that has reached equilibrium, so for example, if we mix a couple of solutions and it reaches equilibrium, it may be, say, red in color to begin with. As you start mixing, it may eventually come down to turn yellow or something like that, or maybe even colorless when it's all said and done, or lightly tinge of yellow. And you may look at this beaker and go, doesn't look like much is happening at this point. It just kind of looks like the reaction's done. And again, it's maybe started really red, and then it ended at like a nice light yellow color. And you're like, I don't see much changing. It's still yellow all the way through. Nothing much is happening. And when you look at it, it may look at like sort of at the big level there that the reaction's over. There's not much happening. But if you were to sort of super zoom in on the molecular level, there is a lot of activity. There's everybody going this way. There's everybody going this way. And there's the forward reaction happening. There's the reverse reaction. It's just happening at the same rate going back and forth. There's a lot of activity to happen for you to look at the beaker, for example, and go, it doesn't look like much is happening. It has been yellow now for 10 minutes. Nothing's really happening there. The reaction is definitely done. But if you were to super zoom in, you would see there's a lot of activity happening to maintain that equilibrium, and that reaction is happening forward way and reverse way happening at the same situation. So two very common sort of misunderstandings of sort of chemical equilibrium. People think equilibrium, it's reached equilibrium, everybody's equal, right? Because it says equal kind of in the name as well, almost. So equilibrium, again, doesn't mean that. When we talk about something reaching chemical equilibrium, we're really referring to kind of like what we've been talking about in the last chapter, the rate, or how fast the forward direction is happening versus how fast the reverse direction is happening. And when it reaches that equilibrium, those two things are equal to each other. And that's why it says, macroscopically, the big picture, it looks static. It doesn't look like much is happening. But on the microscopic level, it does very dynamic. There's a lot going on back and forth. So if we just sort of look at a graph here, this is actually the formation of ammonia. which is what we saw there, N2 plus H2, make some NH3, and maybe a 2 there, and a 3 there. And when this reaction first occurs, we pretty much have, 100% our reactants, as you can see here in the picture, at kind of time 0. We pretty much have just our reactants. We have none of our products present. And as his reaction starts, really the forward direction has to predominate, because the only way that we could get the reverse reaction to occur is we actually have to start making some of these guys. So really at the kickoff of this reaction, we're going in that forward direction. And as we start to make some products, we do see a decrease in the amount of reactants, and we start to see an increase happening in the amount of products that are being made. And at some point, we'll get enough products to be made that the products will start to go, I'm going to head back this way. So at the start, we have the forward direction happening. As we make enough of the products, we will get the reverse reaction basically to kick off. And that will, what we see here in this picture, a continual kind of increase in the amount of products that are being made, a continual decrease here in the amount of reactants that are being used. And what we will see is everybody, the reactants, the products, everybody here, as I badly drew over it, will kind of level off in terms of their concentrations. And when we see everybody start to level off, that is the point where equilibrium has been met or has been reached. And that is the part where the rate of that forward direction will equal the rate of the reverse direction. And what we see here, before I really badly drew over these lines, they were all pretty plateaued. They're all linear, right? Or straight across. And that means that the concentration of H2 at this point, the concentration of NH3 at this point, and the concentration of N2 at this point, they're all going to remain relatively constant, because just as quick as we're going one way, we're coming back the other way. And everybody at that point locked into place where they were in terms of their concentrations. And as you can see from this picture, H2's concentration is different than NH3's concentration, and that's different than N2's concentration. So again, equilibrium doesn't mean that all three of those things are equal to each other in terms of their concentration. What it means is they have now all locked into place in terms of their concentration, and their concentrations will remain relatively constant as this system reaches equilibrium. And again, that's based on the reaction going back and forth at the same rate. Question on that there. Okay, so I think we're towards the end, so it's probably a good place to kind of stop before we get too far into this stuff here. So we'll take a break here. 11:30 we'll have lab.